Okay, 3.21 is pretty much the same thing as 3.20, just a harder, more painful version. So once again, I'm just going to set up the integrals and not actually go through with doing them because it's going to take me all day. We're going to do the same thing, test the energy, time, uncertainty principle, but this time we're dealing with the traveling Gaussian wave packet from problem 2.42. And we're doing pretty much the exact same process, right? We're calculating sigma h, sigma x, the time derivative of the expectation of x, right? And at the end of the day, ultimately everything derives down to sigma h times sigma x divided by the derivative of the expectation of x with respect to time. And this is supposed to verify that this is indeed greater than or equal to the minimum value of h bar over 2. So once again, ultimately, we're trying to find the expectation of the Hamiltonian, the expectation of the Hamiltonian squared, the expectation of x, the expectation of x squared, and finally d times the expectation value of x with respect to time. Now, this one has also been partially done for us, right? Because in problem 2.42, one of the things that we did was we found the expectation values of x, which was equal to h bar times lt divided by m. We found the expectation value of x squared, which was equal to m squared plus 4h bar squared times a squared times t squared, all divided by 4m squared times a, plus h bar squared l squared t squared divided by m squared. We found, well, we didn't find, but from this we can denote that the derivative of the expectation value of x with respect to time is just going to be equal to h bar l over m, right? And then we also found that the expectation value of p and p squared were h bar l and h bar squared a plus l squared, respectively. So the hard part here is going to be trying to sort of figure out the absolutely atrocious integral that sort of this expectation value of the Hamiltonian is going to give us. So in order to find that, we can recognize that, you know, the Hamiltonian in this case can be rewritten in terms of the p operator because we don't actually have a general formula for the energy of the traveling Gaussian wave packet. So we know that h hat is equal to negative h bar squared over 2m times the partial squared of x squared plus v. So in this case, v is just equal to 0, and we know that p hat can be defined as negative I h bar d by dx, right? So in that case, if we rewrite the Hamiltonian in terms of p, then the expectation value of h is going to be equal to 1 over 2m multiplied by the expectation of p squared, and that's, we can just plug that in, right? This is just equal to h bar squared times a plus l squared divided by 2m. Now the hard one is going to be the expectation value of the Hamiltonian squared, because this is going to be equal to 1 over 4m squared times the expectation value of p to the power of 4. And this is obviously a horrible integral, right? We're going to have to take 4 position derivatives on this ugly equation. And one way that we can make this somewhat easier is immediately, right, you should think that, oh, you know, we can make our lives a little bit simpler by switching to p space. But that also means that you have to Fourier transform this horrible, disgusting equation into p, which itself is also sort of a monster, so you're kind of in a lose-lose scenario. But doing the Fourier transform on this and evaluating the p integral afterwards is less painful than taking the derivative 4 times. So let's write out the Fourier transform integral. So we know that phi, whoops, that's an ugly looking phi of p comma t can be written as 1 over the square root of 2 pi h bar times the integral from negative infinity to infinity of e to the negative I px divided by h bar multiplied by psi of x comma t times dx. And I'm just going to write this out and then just sort of give a general rough overview of how to actually solve it by hand if you do want to go down that route. And once again, I'm not going to bother actually solving it. This is going to equal 2a over pi to the power of 1 over 4 times 1 over gamma times the square root 2 pi h bar times the integral from negative infinity to infinity of the exponential of this disgusting thing, negative a times x minus h bar lt divided by m squared divided by gamma squared plus I lx minus I h bar times L squared times T divided by 2M minus IPX divided by H bar. And this is all in terms of dx. So if you want to actually solve this, what I would recommend is that you complete the square for the polynomial that's in this exponential, right? This thing is ultimately going to resolve into a polynomial in terms of x. So I would say, you have to go through the pain of expanding this thing into individual components for x. And after that, you have to use usolve. You have to use usub and effectively try to solve it as an ERF integral. And, don't forget that gamma itself is this disgusting term which we're going to have to expand fully later down the line as well in order for everything to cancel out neatly. I do not ever want to touch this. I solved it once on my notes just to make sure that my thought process was correct. I never want to do it again. It is a horrible thing. I don't even remember what my actual integral solution was. But once again, it's not something that's fun to do. So I would heavily recommend that you either skip it if you're able to, or if you're doing this for homework, to just shove it into an integral calculator. I promise you, your professor will not blame you, or at least they shouldn't. Considering that at that point you might as well just be doing math homework instead of actually looking at physics. But either way, you plug this in, you get the actual answer for whatever this is, get the value for the expectation value of h squared, you plug everything back into this original expression, and you have to verify that the monster expression that this turns out to be is indeed greater than or equal to h bar over 2, and from there you're done with this problem. So with that, I will leave this problem as is and move on.